Good afternoon, everyone, and welcome to this week's Kent Seminar lecture. Today, we are very delighted to have Professor Alireza Talebpour as our Kent Seminar speaker. Professor Talebpour is an assistant professor in the Department of Civil and Environmental Engineering at the University of Illinois Urbana-Champaign. He earned his doctorate from Northwestern University and his master's and bachelor's degrees from Sharif University of Technology. His research focuses on vehicle automation, connected transportation systems, traffic analysis, and traffic flow theory. His work includes developing algorithms to enhance safety and efficiency in automated driving and creating simulation tools for vehicle and communication systems. Everyone, please join me in welcoming Professor Talebpour.
Hello, everyone. Thank you for the opportunity. I appreciate it. So I decided to do it a little bit different. The entire presentation, you won't see a single equation. I decided to keep it at a high level intentionally. This is a summary of about 9 years of research on human automated vehicle interactions. I want to give you overall the sort of a history of where we started, why we started, and how things changed over the years, and how we are essentially addressing the changes that we see every day. So it used to be very easy to do research in this area. You just needed like a simple traffic simulation tool. You assume that everything else is great, and like you're going to have everything in autonomous car, less reaction time, going to have more efficiency, and just run a simulation and assume that, okay, well, everything else is going to get better in the world with autonomous cars. Things have changed quite a bit since that time. So back around, oh, this is interesting. Okay, so around 2013, 14, 15, there was this whole idea of smart cities was becoming a dominant narrative. There was a lot of different variations of it. Eventually, it got consolidated, and you still hear smart cities today, but they're quite a bit consolidated. The key element of, however, of all these notions, the ones that you still see today as well, was the connectivity. And the idea was all these pieces of smart cities, whatever you want to call it, define as smart, is supposed to be connected. So over time, a lot of things evolved. Interesting things that, from our perspective, that is still stays valid was automated car systems, autonomous driving, and traffic flow optimization. And we decided to work on these topics from around 2015, 2016. And then that was like kind of like the focus of the start of this whole story and the focus of the research. So connecting different elements of smart cities is easy, like technology related. You can connect your phone to your microwave, to your toaster, whatever you want to call it, smart. Now you have some version of it you can buy on Amazon. So the challenge was when you were trying to get human in the loop and get humans involved. There were some challenges that a lot of it we still don't know the answer to. So we don't know how automation, connectivity, and AI is going to change the human behavior. So there's notion of like OpenAI is now discussing if okay, a lot of our social norms has to evolve and change. We don't know yet. So that's one question. From a transportation perspective, a lot of elements were predicted that's going to change. Driver behavior was a key factor, roadway safety, infrastructure design and maintenance. A lot of it is still valid, but over the years, a lot of this vanished. And I'm going to particularly talk about what happened to the driver behavior analysis in the presence of automated vehicles. So to address that, the key element was to characterize human automated vehicle interactions and try to figure out what we really want to do about it and how we can analyze if human behavior changes in response to autonomous cars, and if it does, how does it change and how we can capture that. So what are the challenges we faced from day one? Data was never available. It's still, it has got better, but it's still limited. The ones that you see out there are very handpicked. They are promoted to make sure that the company has a great image and also to make sure that the company doesn't get sued. So, and then there's also a lot of data sets that are controlled experiments. I'll show you one of them, but a lot of them happens in test tracks, which they're valuable, but they're different from a typical driving environment. And then the driving logic of AVs has become like a challenge. I have a few detailed slides on it, but it has evolved considerably over the years. We used to have, like when we had the DARPA Grand Challenge 2005, 2007, it was pretty much robotics people that took over and tried to apply everything robotics into autonomous driving. And over the years, that proved to be inefficient and practically impossible to utilize as a pure method, the only method of operating autonomous cars. So the data that was available is still the case, a lot less, but it's still quite a bit like across the board, is focused on training some of these robotics algorithms, or even for the non-robotics algorithms, mostly designed for, the data was shared by companies to make sure that we can, the other companies or the researchers can promote the development of autonomous vehicles. There was no notion of how it's going to change our driving environment. There was none of these companies very interested in it. And then there was the whole idea of dynamic learning environment. So this technology has always been, like since the beginning of it, on extensive and fast-paced development. And what I can get today is very different from what I can get in a few months. You can see that in the rate of like Tesla Autopilot. Every few months you get a new version of it that behaves completely differently. And like what you get today can be different from what you get tomorrow. And that can change the entire dynamics. So sort of that's a challenge to see, okay, how this is going to evolve and how we're going to predict the future of the human elements in the transportation system when autonomous vehicles are changing every day. Okay. So we started by being very naive. We thought that, okay, well, General Motors gave us a car for a competition, and we thought, okay, perfect. This is back in 2016, 17. We said, okay, why don't we run our own experiments? We ran a very simple control experiment. We have 10 people. Some of you might have seen this experiment before. We took vehicle movement data called vehicle trajectory data from a data set called Next Generation Simulation Data Set. It was collected in 2005 in California. I'm not sure if Professor Oyang was involved in that project at all or not, but I think UC Berkeley was quite involved in it back then. So, and we took one, so we said, okay, well, we have two scenarios. One is we ask our autonomous car to exactly follow the speed profile of the data that we observed. And the second scenario, we replace that data with an autonomous car model, and we ask to, kind of like the autonomous vehicle to move like an autonomous car. Okay, this was our own algorithm of autonomous vehicle. That doesn't necessarily mean that Waymo or Cruise or anyone else would have used it. And then we had test subjects following those vehicles. And they didn't know what kind of, had 10 different trajectories, 10 different cases, and 10 test subjects, 100 data points practically. And then we looked into, okay, they didn't know if they're following an autonomous car or they're following a human driver. And all we wanted to do, we wanted to see if there's a difference in the behavior of the test subjects when they follow an autonomous car versus when they follow a human driver. And we looked at the data, and the data was very clear there's a distinction between them. So not in every aspect of it, but we found out that when humans are following an autonomous car, they tend to follow them to get closer to them, and they tend to follow them closely. Our hypothesis was the movement of autonomous cars are smoother. That's why humans are more comfortable getting closer to them. Okay, so and we later on we looked into a few days later. We looked into what parameters can be utilized to capture this observation, because we noticed this, but we're trying to model this to see how we can say, I have a model of the human behavior that shows this difference between following an AV versus following a human driver. And we looked into the parameters. So we utilized something called dynamic time warping. If you're not familiar with the idea, it's essentially a distance measuring algorithm for time series data. It was initially created to distinguish dolphins. So they were recording dolphins, essentially voices under the sea, and they wanted to see if they observed a new dolphin, or it's the one that they already they've already seen. And they were trying to figure out the issue that they had back then, and we have here as well. The duration of the time series was different. And then they don't necessarily have, because the duration was different. So it's like me talking very loud or fast versus me talking very slow and like with a sort of a different sort of pattern, but it's still me, right? So we want to make sure that these differences can be captured. So the same issue we observed in our data. So when, like, necessarily the whole experiment didn't start at the same location at the same time stamp, right? Sometimes there was a shift between the two cases. So we wanted to make sure that those shifts are not going to kind of impact our analysis. Essentially, we cannot just say, I'm going to compare the data points at t equal to 20 seconds in two different data collection efforts. They have to be somehow connected, and DTW would make that connection, essentially just assign the 2 points on 2 time series to each other. You can measure the distance between the two. So whatever you want, Euclidean, whatever measure you want to do between them. It's a detailed analysis. I don't want to go into it. I want to discuss the results. We found that really the only thing that was different was the spacing. So just like what we observed before, like just visually observe that people get closer, spacing was the model that was a parameter that could capture the difference between behavior. And so we did some calibrations of car following models based on a stochastic IDM. We showed that, okay, a stochastic IDM can capture this difference, but a lot of the traditional deterministic car following models cannot really capture this behavior. Okay, so this is us being naive. This is us assuming that, okay, we did one experiment. Okay, fine, it looked like a lot of effort, but now we have a lot of interesting data points. So that didn't really age well because as we started collecting more data in a real world setting, we noticed that what we collected was not really what is supposed to happen or is happening, at least in the field. So we noticed that there are a lot of the things that we thought that these are definite findings in our controlled experiment we do not see in the real world setting. So we collected a lot of data. We collected a whole data set called third generation simulation data, which has several hours of vehicle trajectory data in Chicago and Washington, D.C. We noticed that, okay, a lot of behavioral differences between this data. We had some we had some Teslas, we had some level 1 adaptive cruise control vehicles, and then we noticed that their behavior is different from what we observe in the controlled experiment. There are also some higher level automation data set, like Waymo Open data set. The Lyft level 5 data set is also available, but that's a little bit old, and Lyft does not have autonomous driving anymore, so that's like a few years old. So these are all from Waymo Open data set. So they provide a lot more diverse sort of data structures. We had, however, an issue when we were looking at the Waymo Open data. So Waymo Open data set seemed to be like a perfect scenario case to do the exact same analysis that we did with our own controlled experiment. But there was an issue with Waymo Open data set. It was too short. All the sections. This is not designed for what we are trying to do from the traffic flow perspective. It's designed to train autonomous vehicles. So they share this data. They run a competition. If you're interested, actually, I think the prize is $50,000 or something. So it's a decent competition they run every year. They share this data and they expect people to predict the movement of other cars or test the new perception models to detect the objects. So this is the intention of the model. So for that reason, the data is either 10 or 20 seconds long. And it has very limited field of view. It's certainly just whatever the car can see. So if you notice here, like the car can only see like 2 cars ahead, and for sure there are more cars in front of it. There's one more thing that there was more issue with this data, and that was we didn't know if we can trust it. So obviously, our assumption was Waymo does not really want us to know exactly how they operate. So there might be random noise in the data to kind of like hide what the actual performance was. It was definitely hand-picked data. There's no way Waymo would share something that is sort of a safety critical situation or something that they can be sued. So we want to make sure that their data is correct, and we want it so that we can use it we can trust it and we can use it. We also wanted to be able to have longer interactions. So we flew to Phoenix. We hired a helicopter. We found some Waymo cars and we start following them for about 3 hours. So so this happened like about 100 to 200 meter altitudes. And so this is the Waymo data that we're following. And what was happening essentially was we were following this vehicle as it goes through the traffic with a helicopter, and we were able to extract the trajectory movements of this. So in all sort of different naturalized scenarios. This is like someone is, because you can get these. I know some of you have tried this in Phoenix. So I know Errol and Ramez have tried it. So, but you can technically just get it like Uber getting it. So we were just following that car as it goes from picking up someone and dropping off someone at the end. So both downtown Phoenix and Chandler, which is a suburb of Phoenix. So this is like a summary, like a sample of that trajectory. So this is color-coded. One is the Waymo data as it goes through traffic and different traffic signals, but it goes through the entire city. So we have a very long trajectory of Waymo, and throughout this, it interacts with many different cars. So so we did an analysis of the accuracy of the data. We are roughly almost most of the time within 0.5 meter accuracy. So it's fairly good given that our pixel sizes are 0.3 by 0.3 meter. And then we run like essentially a comparison between what we collected and the Waymo Open data set as a proof that, okay, we can trust the Waymo Open data set for this analysis that we want to do. Okay, even if there might be noise in it, we can still trust it to that level. So let's dig into some of these results that we found. These graphs should have bar charts. They don't show up. It's a Mac Windows issue. So, but this is the fitted curve. That'll work to some level. So this is the human is when humans following another human. AV human is when an autonomous car follows a human driver. And human AV is when human driver follows an autonomous car. So when there is an autonomous car involved, the spacing is sort of tilted to the left. Less spacing was observed in general. And then you also, it's a much narrower distribution. Okay, so I'm just looking at it like just visually. Relative speed, very similar thing. So Waymo cars were very strict to the speed limit. And because of their very smooth speed adjustments, they actually resulted in a much narrower speed distribution compared to when humans were following humans. So we also looked at the lane keeping analysis. You wanted to see how Waymos stay within the lane. If they stay really in the center, they are a little bit moving to the right versus how humans behave. Waymos are roughly always in the center. They are about 0.1 meters to the right on average, but they have a very rough, nice like normal distribution of the behavior, the blue line there. And then human drivers are sort of weird. They're all over the place. But what we did was we actually fit a Gaussian mixture model. And we noticed three distinct behaviors. We had like a very good human drivers that stay in the middle, pretty much. And we found two other groups that would kind of like move around in the lane. Like essentially some of them more tilted to the right and some of them more tilted to the left, which was an interesting observation. And this comes back, I'm going to come back to this when I'm talking about lane changing analysis. So Waymos were clearly performing better lane keeping, which is expected, right? So we also did lane changing analysis. And so there are 4 categories. So I want to just go over some notations quickly. A is called active vehicle. That's the one that's changing lane. O is the opening vehicle, and C is the closing vehicle. Essentially, you're trying to change lane between the two. The distance between A and O is called lead gap, and the distance between A and C is called lag gap. So in other words, the idea is you need to have enough space between your vehicle and the one in front and the one in the back in the target lane so that you can find your way in and make a successful lane changing. So there are 4 cases. We have AV acting, AV is the acting vehicle, it's changing lane. We have a case that there's no AV in the data set, obviously, the lane changing involved. We have AV as the opening, and we have AV as the closing. Okay. So, like some lead gap analysis, very interestingly, when we are talking about lead gap, the lead gap is the distance from essentially the lane changing vehicle to the vehicle in the front. And for the Waymo cars, they almost keep a very constant lead gap throughout this lane changing maneuver. The humans, however, tend to speed up, close the gap, and then once they change lane, they would slow down and increase the gap. So, and I thought about it, I said, that's how I change lane. I actually speed up, I get to the lane, and then I start adjusting my maneuver. So Waymo cars are slightly different from that sense. And the lag gap, it was a little bit different. So typically, so the lag gap, the human drivers tend to try to increase the lag gap. And what happened with Waymo cars was with Waymo cars, the gap would decrease. Part of the reason for decrease is because Waymo cars do not exceed the speed limit. So essentially, the car that is following them would have to slow down, and that closes the gap. But human drivers tend to kind of like speed up and increase the gap in general to make sure that the car behind is not too close. Okay. So overall, if I want to just sum this lane changing analysis up, like human drivers decrease the lead gap before entering the target lane and then increase it, while the autonomous cars stayed like at a very sort of constant speed. And the lab gap, the autonomous cars really didn't care about, as long as it's safe, they didn't care about how fast they're going. They would stick to the speed limit, and the vehicle behind would close, so the gap would decrease, versus humans would actually adjust their location. This has actually beautiful contour map, which you don't see. But we did using dynamic time warping between the difference between the trajectories of the lane changing in these cases. We actually clustered them. I won't go into details of how the clustering, the whole thing works and how we formulated it, but that was very interesting. Almost all the observations of the autonomous car, except one of them, fit into this cluster 1, which is very small lead gap and very small lag gap. That simply means that autonomous cars were very good drivers. We had human drivers there as well. So they tend to behave very similar to very good human drivers. And we had human drivers that were all over the place. Okay. So they tend to be very robust, very good drivers. But they still behave very similar to human drivers in many of these scenarios, which gets me to my next topic. But we also did some analysis of lateral acceleration on the turns, like if you're doing right turn or left turn maneuver, how much acceleration is being imposed on the passengers. Human drivers tend to do better, so the Waymo tends to have higher lateral acceleration. However, human drivers had a much wider standard deviation compared to AVs. So AVs had typically higher lateral acceleration, but they also had sort of a narrower distribution. So this gave me to the idea of the changing landscape. So this is what, I don't want you to really read any of these. This is intentional, because this is how an autonomous vehicle software stack would look like back in 2012 to 2015. Complete robotic space. You have a perception system detects the objects. You have a tracking module. The tracking module feeds into motion planning, path planning, and then you generate a safe trajectory. You have a controller that follows it. This failed pretty much. Not entirely, but people got to a point that, okay, this is not good enough because there are too many edge cases that you cannot plan for all of them. So what can we do about it? So back in 2014, NVIDIA did a test they called it end-to-end autonomous driving. What they did is they took their car and they drove around for 6 months. They collected camera data and steering, throttle, and brake data. They just did that. It's just everywhere, like in the snow, in fog, everywhere. Just utilized a very simple convolutional neural network that the output of it was what should be my steering, what should be my throttle, what should be my brake. And it worked very well. If I just forward, it's like a little longer than it would be. So it learned to drive by itself. But it was very limited. It was very limited to the scenarios that they collected data. There was no way of, and the size of the neural network was not big enough to capture very diverse scenarios. And this thing died essentially back in 2014, 2015. Everybody, I remember a tweet from one of the very prominent autonomous driving CEOs that said, if you think that Waymo, back then Google, didn't try end-to-end autonomous driving and ditched it, you're sadly mistaken. Like that was a tweet, like they believe that this is not going to work. Up until very recently, where we started to have foundation models and the attention and the transformers, which scale well. And this is what everyone else is doing now. So they move, Waymo, Tesla, all of other ones are moving, shifting from having a robotics-based platform dominating the whole software stack to foundation models driving, which is essentially an extension of end-to-end what NVIDIA is doing. It's not perfect. This is one example, very recent example of the Waymo that doesn't detect, that's uncomfortable, right? Doesn't detect the pothole, but they learn and you know, next time it will recognize that pothole next time they train it. So, and so this is changing the way we're essentially analyzing. So what happens here is, initially the idea was you have a CAV design that is going to influence human behavior. That's everything, all of you have been doing up until now. And then since human behavior is going to change, you're going to have different traffic patterns, different high-risk maneuvers, and then you have to update your CAV design, which might not, there might be an endless loop with no equilibrium. That changed into the whole idea of I'm going to learn from what I observe from human behaviors, and because I observe from human behaviors, I pick the good ones. So I drive like a very good human driver. So I have design consistency, and because I drive like human drivers, my impact on other human drivers is very minimal. So this can reach an equilibrium point. What is the downside of this? We are teaching autonomous cars to behave just like humans, good humans, but still humans. So there's no notion of efficiency, anything. Safety is a key part. That's a good human part, but there's no notion of efficiency. Everything we were hypothesizing, like, okay, we're going to have 3 times more cars going through per lane every hour. That can't happen. It's just drive just like human drivers. It's not going to drive any differently. So, but this provides a lot of interesting research opportunities. So we have a lot of things, I put pedestrians, but it's really no motorized modes of transportation. This is a challenge for almost everything. If you get a Tesla, they don't really know how well to interact with scooters, for instance. That's something that's a very, that's an area that's very active. Also, for rural autonomous driving, animals and like wildlife, those are challenging. Not enough data. So like typical foundation models would not have enough data to be well trained on that. We have infrastructure design. So a lot of the ideas that, okay, we can update our infrastructure to, we don't need more lanes, or we don't need different sort of roadways or intersections. Those are all out the window. So if you're behaving like humans, you have to think about like humans in the loop. And then you have simulation platform. I don't want to make a very bold claim, but a lot of the things that we do at a simulation level for autonomous cars practically is out the window, because they are behaving like humans. There's no point in modeling them as a robot. There's no motivation for that. So I'm going to leave you guys with those 3 topics, and thank you so much. Sorry, I'm 4 minutes over time. Yeah. Yes.
I had a question. When you said that foundation models are replacing the classical robotics stack, do you mean just the perception part, or like?
No, it's the whole thing. There's no perception stack or anything. They're just your. So in the most, let's call it most ideal situation, what you're focusing on, getting raw sensor input and getting the output as a steering, throttle, and brake. That's like, there's nothing in between. There's no perception. There's no motion planning. There's nothing. It's just deciding based on raw sensor input. The ones that are a little bit more sophisticated, they create some sort of they fuse the sensors initially before feeding it into the model. So you take an autonomous driving course today, they will teach you about perception, motion planning part, localization. None of them is happening anymore, pretty much. But we can't do much about it in our setting of academia, because we don't have enough data, we don't have the compute. All we have is the talent, which they also have. So we can't keep up in that regard with them. But there are areas that we can focus on, obviously wildlife detection and response. So that's why they never completely ditch the robotics aspects of it. They still exist, but they are not the dominant part anymore.
Oh, Waymo and Tesla and all these big.
Tesla for sure is completely end-to-end. The latest version of Tesla is completely end-to-end. I don't know about Waymo for sure, but I've heard a lot of rumors that Waymo has also moved completely to end-to-end and like movement. Yes.
One more thing. This is like an open-ended question, but we're teaching these vehicles to behave like humans, and just like you said. What now? I mean, what is the benefit besides not having?
Oh, the benefit, from their perspective, their business model is to give you your time back. So you would pay them to get that. Essentially, you're paying them to get your time back. That's how much your time worth. That's it.
I don't know, safety and like stuff.
Well, the safety is also there because they are supposed to drive like a very good human driver. But from the efficiency perspective of like we were talking about, okay, this is going to be super efficient and we can have, instead of like 1,800 vehicle per hour per lane, now you're going to have 3,600 vehicle per hour per lane. I do not believe that's going to happen. They're not going to disturb. Maybe if they have a lot of them, they would start to do that. But in the short term, I do not believe they are going in that direction. They're behaving just like human. I think the motivation to behave just like human is because since they have started that, they have had a lot less safety critical issues. I'll give you one example. So Tesla, the version 12 had one disengagement every about 60 miles. With the version 13, it is about 752. So since they moved from like robotics to end, that's how much improvement you've got. So part of it is because humans around them do not expect them to behave in a weird way. So it's more of a natural driving environment for them. And part of it is they got better, of course.
Thanks, Alireza. This is very interesting. I remember those early things you're talking about. That's what a lot of the people I knew working in this space when I was studying were doing. And now it's interesting to see how far it's came since then. First, I think one important thing to note related to Mohammed's question is that for safety, the main causes are distraction of crashes, are distraction, impairment, speeding. All of those will be completely eliminated.
Right.
So right there, this will be much safer. But I guess the question is, from my end, I'm always interested in how the liability will work. As far as I know, if you're driving your Tesla and anything happens, goes wrong with the autopilot or it shuts off, there is no responsibility held by Tesla for that. You will be responsible as the driver still. So you can't really reclaim your time yet unless a court finally says that the driver will not be responsible for the actions of the vehicle, right? Is that right? And where is that kind of side of the research? I know that's not your area, but where is that kind of policy side now?
I remember reading like the user agreement in the Waymo one app. That one also says it's an experimental thing. If you get hurt, it's on you. You can't sue us or anything. You acknowledge that. But eventually, I think for Waymo or someone, like they accepted that this is their liability. They're giving you a ride. So you're going to be liable. But Tesla still gets sued, even though they're technically saying that it's on you, but they still get sued. So because if you're distracted, if you're activating and you go back in the backseat and asleep, it's on you. But if it does something weird and you hit something, people will still sue them. I'm not sure where it goes, but because they're never that kind of like settlements are never public. You never know what they are giving people to.
Right? That's been
Right.
constitutional that you can't
Right.
do the gun maker because somebody killed somebody with a gun, even if it's accidental,
Right.
right? So
Right, but I'm pretty sure all of these companies have put money aside to settle the lawsuits. And unless they do something like Cruise, which I'm not sure if you guys heard, they hit a pedestrian and then dragged the pedestrian for several, I think 15, 20 feet or something under the car. Unless something like that happened, I mean, typically they would just settle right away and just, yeah.
Yeah, I don't see it. I don't see myself sleeping or working while I'm driving until somebody says I can't be sued if any accident happens while it's on.
Yeah, but like for me personally, like for Tesla, for instance, I could, before, when I was driving, even with adaptive cruise control, I could do about 4.5 hours like continuous, and then I had to stop. With the autopilot, I can easily do 8-9 hours without, yeah, because I'm not doing anything really. I'm looking at the road, but I'm not engaged. So it's a lot less boring and tiring, essentially. You can try it.
I just had a quick question, because you showed that loop where every time we need to kind of like remodel because there is like new high risk scenarios, and
Right.
we need to understand how they affect the human behavior. But I was thinking, if we reach the point we don't care a lot about the efficiency, as you mentioned, maybe we are training the autonomous cars to drive like humans, then why don't we just train them on like very the most extreme, like most risky scenarios? And I know that way we will not be efficient, but I mean, we don't care so much.
The challenge that all these companies had, is still have, but the challenge they had, like these, they call them edge cases. They are rare and they are unique. So I remember like back then, I think it was Waymo or another company, they created a simulation explicitly for this. They were saying, if we see a high-risk scenario on the road, even though nothing happened, we are going to create 1,000,000 different scenarios out of it, so that we are going to hit someone and kill someone or something in the simulation, so we can train for it. It's a curse of dimensionality. Like, those things are so rare, and then the consequence is so huge. Like, you can't really assume that I've seen everything. That's what they're having issue with. And someone like Tesla accepts the risk. You say, you know what, I'm okay killing a few people maybe, or getting some people get hurt. I mean, they're from the beginning, when they had the very initial versions, like they couldn't see trucks and the cars were running, like hitting trucks and everything. They accepted that and say, okay, we can improve off of those, right? So yeah, for long there was no good answer to that question. But I think now what you're doing is they're collecting data from essentially every Waymo car or every Tesla that you see on the road. And now they have a lot of edge cases that they're training for. So I think that's part of the improvement for now. Yeah.
I noticed that I never saw any company doing any sort of autonomous driving for shared, besides obviously ride hailing, but like a bus, maybe a bus rapid transit or rail or whatever. Do you see this immediately trickling down to like public transit, or like do you see an opportunity that's basically untapped? Maybe we can actually have an efficient.
There are some companies that do some sort of public transit. There's one from Michigan. What is the name of that company?
May Mobility.
Yes, May Mobility. Thank you. So May Mobility is one of them, but they never actually. It's about the profit. So May Mobility, I talked with the CEO. Was presenting in Michigan. They spend a lot less money because they have a lot less challenges, because they have like operate fixed route. They can figure out everything that can happen around that fixed route, but the profit margin is also very limited. One thing that everyone was hoping to happen was autonomous trucks, 18-wheelers, which for some weird reason, they had so many of them, but there's only one company left. So everyone else stopped, even Waymo stopped operating them. For some reason, they found challenging. I don't know why they stopped, but it seemed straightforward, because this long haul, it was just supposed to cover the interstate portion. But for some reason, that didn't work either. So I don't know why, or maybe the business wasn't there. So I'm not sure, but there's only one company left that does that. So.
Thank you, Professor, for your presentation. I would like to get your opinion on what do you think, or if there is any agreement into what exactly full self-driving means? Do you think an average driver represents full self-driving? Because as a curious fact, I think an ICT student, at least one ICT student, has a car accident per year. And I don't think that would be acceptable for any company right now. So I don't know what is the target of this full self-driving concept. You said you can work without these engagements for 9 hours, but is that considered already full self-driving?
No, I think for me, full self-driving is when I don't have to look into outside of the window. So that for me, that's full self-driving. So when I don't have to when I'm just like a passenger, like I'm sitting in a passenger seat, I don't care about what the driver is doing. That's for me, that is a full self-driving. So in whatever form or shape that is, with or without a steering wheel or anything, as long as I don't have to look outside, that's what I call full self-driving. You're not there yet, but I actually this time I'm very hopeful. In a couple of years, we're going to see them. Like you've seen a Waymo car, you really don't care. At first 1-2 minutes, it's exciting because there's no driver, but after that, if you would just automatically stop losing focus and start looking outside just like someone else is driving you. That is full self-driving to me. The only issue they have is they kind of scale it up because they need to go from city to city. That's challenging. They figure that out, then that's full self-driving completely.
On the slide that you mentioned that if a car faces a pothole in an intersection, most likely it will memorize, and next time it goes through the same location, it will have to reduce the speed by reinforcement learning. But how would you say we could manage to have this behavior when you encounter a new scenario?
Right. They're not memorizing location based. So the idea is like I'll go back to original end-to-end. So that pothole has a certain look to it, right? The idea is, can you learn from that look to see there's a pothole? Because you see a pothole, you fall into it. Next time you see, kind of. It doesn't have to be the exact location, right? So there's no process of like memorizing a specific thing. It is more of memorizing what something that is not supposed to happen looks like, right? So these attention-based models are really good at this. So that's part of the reason this is working very well now.
One last question, if I may. There are many videos showcasing how some of these autonomous vehicles perform really badly under adverse conditions such as snow, because maybe the most speed might say 60 miles per hour, but if you try to go at that same speed in snowy conditions, that would be maybe too dangerous. So how do you think would be the best way to try to address these specific conditions? Do you think we need more sensors for weather?
Yes, you need more. For them, I'll give you one example. Like no one knows the answer to that question, by the way. I think companies try different. Waymo does a lot of testing in Michigan, Detroit, Ann Arbor. You see a lot of Waymo cars. They collect a lot of data in the snow. No one has been able to really figure it out. But I'll tell you what a lot of these companies do. They look at human drives around them. Like if you have a Tesla, if it's snowing, it reduces the speed it's a highway 70 miles per hour, right? There's no one around. It will reduce its speed like to 20, 25, 30, which is scary. But then as soon as it sees another car, it starts following that car. So it's sort of like built in manually that, okay, I'll trust other people and what they are doing. So I'll just sort of go with them. But there's no answer. No one really knows how to do it. There's still a lot of issues. There's glare from the sun that they still don't know what to do with it. There's still issues. It's not a done problem, but it has improved a lot for the past 2 years. Like it's a huge improvement in quality of autonomous driving. Thank you. Thank you.